Okay, so we're now going to move on to using SPM. So this is just a quick figure here to show you the pipeline of what we're going to cover today. So we take some functional data that we have, we pass it through some pre-processing steps, which involve basically dealing with artifacts and normalizing to standard space. Then this afternoon we take these smooth normalized data and we fit a model to the data. And that gives us some estimates, some parameter estimates, which are the measure of the degree to which some voxel or region is correlated with our task condition of interest. And then we compare these responses between different conditions. Because bold isn't quantitative, we have to compare them. And then we produce a statistical map and apply multiple comparisons correction. So this morning, the rest of this session, we're going to be focusing on pre-processing the data, and this afternoon then we'll look at modeling. Okay, so if you haven't already done it, you need to copy the data over to your home account. So CP -R can be capital R, home SPDPOD, SPM course 2017, and copy it to your home directory tilde. And then you can CD, change directory into the directory, and type ls if you want to see the folder. So let me just do the same thing. So I've got a different version of it because obviously I don't want to write over the version you'll be copying. So we type in ls. Oh no. It's very strange. I created the file. Okay. So CD SPM course, type in ls. You should see our file for T1, it's our structural image, our task, folder with some ROIs, and some folders for group analysis, which we'll do tomorrow morning. Okay. So what's the point of pre-processing? Oh yes, so here's a bit of data about the task we have. So in the folder you have a structural image, which has the T1 and the functional data. In the scanner, people did a task for about 10 minutes. The task was a very simple motor task where they moved a joystick where they were instructed to, or they got a free choice to move. The repetition time, so the time required to collect one volume, was 2 seconds. The number of volumes was 300 volumes in the time series. The number of slices was 38. And the slice order was interleaved ascending, so we collected slice 1, slice 3, slice 5, and went back then and collected the slices in between, so 2, 4, 6, and 8. We'll talk a little more about slice timing, but this order is preferred by physicists because it avoids crosstalk between slices, because you leave a gap, you skip over one slice and then go back and get it. But from an analysis perspective, it causes problems because adjacent slices are sampling the bold response at half a TR apart. So let's say with a TR of 2, as we have here, the adjacent slices are actually sampling the brain at a second delay, different from each other basically. Okay, so the aim of pre-processing is to take some noisy data in native space, which is corrupted by movement, because people, no matter what you ask them, they end up moving a little bit, and correcting for the motion correction and normalizing standard space. Additional steps which we'll also cover, which generally are almost always used, are slice timing correction, to correct for this timing difference in sampling of the bold response, and co-registration, which is where we align a structural and a functional image together. Okay, so, I thought I'd change that bit. So we're going to open SPM let's change this to SPM 12. (2016-0310). Okay. So first thing I'm going to do, let's open up SPM. So we can do this by typing SPM -12 2016-0310. And this will take a couple of seconds. While that's happening, I'll show you this. So you'll see 3 windows. This is the command window. Red is for pre-processing. This section here we'll be focusing on this morning. Blue is for modeling, first level and second level model, which is what we do this afternoon and early tomorrow morning. Green is for exploring the results we'll use today. And then there's some miscellaneous tools down here at the bottom. And we'll use some of those for quality control and resetting the origins and things. Okay. And so when we select buttons, we'll get often an option, we'll get this kind of batch window opening. And we're going to go through this in a second. But in essence, anywhere you see an X means some data needs to be inputted for the script to work, for the process to actually be able to execute. And we'll come back to navigation in 1 second. So SPM is being very slow to load. Let me just... Oh, sorry. So you see this window should pop up after a while. If you click fMRI. Okay, so this is the SPM interface. So with the control panel here, so we'll be focusing on pre-processing this morning. This afternoon we'll focus on this section here, which is modeling. There's a graphics window which will show results, and this terminal here shows you progress. It's like a progress bar here, it appears during pre-processing, but also when we look at results, it gives us some extra options about threshold and things like that. Okay, so the first thing to do is let's have a quick look at our images. So if you click display, sorry about the slowness, you have this interface here. This is the navigation window. So it tells us in the directory it's in, the directory one level up, and we can move through previous directories here. SPM is always listed at the top here, which is quite useful later on. On this side, we navigate. So if I click into ROIs, if I want to move back up, remember CD space dot dot, we can just click on the dot dot, and that moves us back up. On this side, we select files. So if let's pick the T1, it appears down here. We press done. And this should display the T1 image. Okay, so it's the T1 image. It gives us some information about the dimensions. It's 192 by 196 by 183. The image is basically just over 1 by 1 by 1, 1.1 by 1.1 by 1.1. And there's an origin coordinate, which is the coordinate 0, 0, 0 in the image. Now, we'll come to this in a second, but one of the first things you have to do for SPM is set the origin at the anterior commissure. Just so you know, this person was wearing an EG cap in the scanner, which is why you see these little weird bumps. Okay, so with this image you can click around. So let's return to... We'll come back to this stuff in a little bit later on. So the first thing we have to do when we pre-process the data is reset the origin. This makes sure that all the images basically are sitting in roughly the same position, with the anterior commissure sitting fairly close to the coordinate 0, 0, 0. We then do slice timing correction. That's what we're going to do in this lab, where we correct for this variation in the time of sampling of the bold response. We'll then do realignment, where we correct for volume to volume head motion. We'll co-register the images, so we'll align our structural data with our functional data, and then we'll normalize our data to standard space, and we'll primarily focus on this method using the intermediate structural image. Finally, we'll do some smoothing, and we'll do some quality assurance, and then we'll move on to doing some batching. Sorry, these slides have also been used for MSc students, so this says the mini project, which obviously isn't for this case. Okay, so why do we set the origin of the images to line the anterior commissure? Well, it's because of this problem known as the local minima problem. As you move images together, you have to have some measurement of their goodness of fit. That could be information theory, it can be the mean square error between the images, various approaches. The problem is that will fluctuate as you move the images in 3 or 4, in 3 dimensions. So here we have an example of this thing where we're trying to get this image into, basically want to minimize the difference between these images. So imagine we start with this position where our images, this isn't necessarily the clearest example, but Chad has to get to see the global minimum, suggesting that's where the images are perfectly aligned or very closely aligned. So if we have an algorithm that moves Chad along to the left or right and stops when it feels it's found the best solution, if Chad starts all the way out here, if Chad moves to the left it starts to go this, yeah, so if tab moves to the left, we see basically the algorithm's going, oh, it's getting better. The mismatch between my position and where I want to be is better. So this is a bit like moving the image together. They start to look like they're closer and closer in position. And then as I keep going, it gets worse again, and the algorithm might go, okay, I'll stop there. That was obviously the best solution. Alternatively, you can go this way. And again, it gets better and better, so don't go head in the right direction. The mismatch, if this is mismatch here on the y-axis, is reducing. And then it gets to here and goes, oh, it's getting worse again, so it stops. So both of these are what's called local minima. So the algorithm searches the space as it moves and measuring the mismatch here on the y-axis. It might find a local solution where if it moves any more to the left or right, the results get worse, and so it just terminates. This is, I found the best solution. However, if we move the two images closer to each other, so we're bringing Chad closer to the global minimum, which is the overall best position, then there's a much smaller chance the algorithm will fall into A or B, because it'll test both directions, and it goes, okay, we're going off here, it's getting better, it's getting better, it's getting worse. What happens if I go to the, oh, it's getting better, oh, it's getting even better, oh, fine, it's getting worse again, so it stops here. So by bringing the images and setting the origins at the anterior commissure, the images are already basically aligned to each other, okay? Just want to check this is recording correctly. Yeah, it's fine. Okay, so the images are basically aligned to each other. So this is the anterior commissure. It's this position here. And we basically want that to be pointing to this point here. Now, I think on the next slide I have a zoomed in version of it. So the anterior commissure is this location here. It's this little bridge here on this, the axial view. In the coronal view, it's this point in the middle, and there's a kind of a little mustache across here you can see, hopefully. That's here at the end of the fornix. Okay? So it's that coordinate there is the local is the anterior commissure. So we need to set the origin to that location. And we use that using display in SPM. So let's do that now, and I'll take you through the steps. So here you can see in red, there's some coordinates, intensities, tells you the intensity, this tells you where we're pointing to. Here you can change the position, and this is where you reorient the images. But in SPM 12 it's slightly easier now, so let's move to SPM 12. Okay. So we have this image, and we click origin. That tells us where the origin is. So I think the origin is going to be roughly in this location here. So I click roughly here, come midline, and if I click full volume, I can zoom in a bit. Okay, and if I go to about there, now this is an SPGR rather than a MP range, so it's not as clean as it could be. And I think that's the anterior commissure there. Okay. Now, for those who want to replicate it, I put in minus 10.8, 31.6, and minus 29.4. So let's just do minus 29. That's probably close enough. We'll say minus 32, and we'll say let's say 11. So 11, 32, minus 29. That's where I think the anterior commissure is. You click Set Origin, and that now sets the origin at that location. The view will go a bit weird. And then you click Reorient. This should give us the option here. It's a little bit slow. And this is the image we had before, our T1 image, which we select. Oh, I've selected it. Right, so we can select it again. Okay, so you can navigate here. So this is going to apply those transformations to this T1 image. It'll ask me, do you want to save the matrix? I'll say no. And the image should see a little bit of work happening, and the image should redisplay. And if I click on origin now, it's now where I want it to be. Okay. Now we need to do the same thing for the fMRI data, but that's a little bit more complicated. So if you click display again, This time we click task. And what you'll immediately see, hopefully, is that the image is much blurrier, much harder to tell the location. The key thing is it doesn't have to be perfect, it just has to be roughly in the right location, right area. And actually, I'm going to move a little bit further forward, but not much, just to demonstrate. So actually, this isn't far off. Ooh, come back medially. Okay. So in my case, I'm doing I'm doing 1, 4, and 0. Oop, oop. So I'm going to just do a slight adjustment. Select reorient, sorry, set in origin. And now click reorient. Now this is the important part. SPM doesn't read 4D image files. So if you know, the fMRI data is stored in a single file with 300 volumes. It's a 4D imaging file. So we get rid of that first. Click on it to get rid of it. And we have to filter. So the filter is, you put a little hat, it says it starts with something. So only show things that start with task. Press return. That gets rid of the T1 here. And then we say 1:300 to show me all 300 volumes. And they're all here. Okay. And then you right click, select all. If you accidentally click on some of the images, just click them here and they'll disappear again. You can redo this. So little hat says start with and then task, and then the dot star means you can end with anything you want. And then 1: says 1:300. Colon just means 300. So 1 to 300. So you see 1, 2, 3, 4, and then you select, right click, select all. So this is going to take the transformation we've worked out for the functional data and apply it to all the volumes in the time series, all 300 volumes. That way they're kept in perfect register with each other, that we've not adjusted their relative position to each other. And again, this will take a couple of seconds. We won't save this. No. Okay. So we've done that. This is the old method. We have to invert values and all sorts of stuff. It's much, much easier than it used to be now. Okay, this will show you the idea. Okay. So once that's finished, we'll move on to the issue of slice timing correction. So you can see here the progress bar going through. It's a little bit slow, it has to be said. Okay, let's talk about the issue of slice timing correction then. Oh, no, that's one way I changed it correctly. Okay. So once the data is reoriented, it's time to do some pre-processing. So the first thing we want to do is correct for the slice timing variation. So if you remember what I said is we've acquired the data, and although we're acquiring volumes, they're really actually being acquired in slices across time. So in a 2-second repetition time, we're actually acquiring data for different regions of the brain at different time points. So here, for example, if we have 8 slices, we acquire, with an interleaved acquisition, we acquire slice 1, then slice 3, then slice 5, then slice 8, and then we go back with and get 2, 4, 6, 8. So you can see actually 2 and 1 are sampling the brain 1 second apart. Slice 2 and slice 1, which are adjacent, are actually sampling the brain at a different point in time. The bone response is already much later at slice 2 by the time we measure the data than it is at slice 1. You can see that here. So we collect the data here for slice 1, and then slice 2. So volume 1, volume 2, volume 3, volume 4. But when we go to slice 2, it's volume 1. Oh, our second slice is just here. So actually this is our first point. We're already at the peak of the response, and then it drops again. Whereas slice 8, which is up here, which is two TRs later, sorry, it's a whole TR later, we're sampling the polar response. So actually the shape of the response we've got is quite different at each of those points in the brain. And that obviously has an impact on our sensitivity to analyze to the data. So one thing we can do is we can reslice the data so that the volumes represent the signal as it would have been if all the data was acquired at one point in time. And that's what slice timing correction is. So this is just to show you, you can do other things like modeling the data, but in essence we're going to reslice the data or interpolate it. So this is if you basically have the data acquired top slice first, you see differences. If you bottom slice first, you have enhanced sensitivity here. If we reslice the data as though it were acquired at the same time, you see a change in sensitivity at these points. It's particularly important for event-related designs where timing becomes important. For block designs, it's not such a big deal because the timing difference we're talking about are sub-TR, so less than 2 seconds generally, maybe 1 second difference in timing. So that's not really a huge problem. Typically, we try and engineer to be no more than half a TR of correction. So if your block's 30 seconds, a 1 second difference on the timing makes very little difference in the model fits. But for connectivity and event-related designs where timing is important, this can have a big impact. So let's go and do that now. Hopefully the origin setting stuff is finished. I think it probably is. If you want to check, you can always go here and it'll tell you if a process is still happening. Okay. So let's begin by clicking slice timing correction. And this will open a batch window at some point. So as you see, anywhere where there's an X remaining means some data has to be inputted. So the first thing is we'll select data. Say a new session. And we have to specify the data. So this is going to be our task data again, not our T1. So we're just correcting the functional data. So again, little hat, task. Hat being shift 6, by the way, 1:300. And we select all. Done. Okay, and you can see here there's 300 files listed, and the 300 files are listed here. Okay. So the number of slices, so if you remember on one of the first slides of the talk, the number of slices is 38. And the TR is 2. So we just have to give it the relative information about how long we acquired each volume for, how many volumes were there, how many slices were there per volume, and when were they acquired. So it then can work out how to reslice the data. So the time of acquisition, as it explains here, is the time it actually takes to acquire data. So within a 2-second TR, we're not acquiring data all the time. There's a little gap before the next volume starts. And it gives the equation here. It's the TR minus the TR divided by the number of slices. So click specify. And then we see, once it gives us the option, we say 2 minus, open brackets, 2 divided by 38. And we get 1.947, something like that. And the last thing that we need to give it the slice order. And again, SPM down here at the bottom gives you some information about the way to encode that depending on what, so interleaved, bottom up, interleaved, top down. Or ascending, descending. So the most common method ones we have in the IOP are interleaved ascending, interleaved bottom up, or descending top down. So this one here. But in this case, our data was interleaved ascending. So it's 1. So as the code says below, it's 1 going up in steps of 2 to the number of slices, and then 2 going up in steps of 2 to 38 to the number of slices. So you can see 1, 3, 5, 7, all the way up to 37, and then it goes back and gets 2, 4, 6, 8. And the reference slice is the middle, is the slice that remains stationary. Everything else is adjusted around it. This should be the middle slice in time, because that means no slice is adjusted by more than half a TR. So in our case, I'm going to say that's either slice 37 or slice 2. I'm going to say slice 2. The downside of that is it's a slice we don't really care about much, so we are adjusting areas we care about, but it's better to do that than to adjust some slices by more. The final thing is it's going to give you a prefix A, which is for slice timing. You can change that if you want to, but that's it. If you want, then you can click File, Save Batch, or you can just click the disk, and it'll ask you to give it a name. And we're just going to save it as slice timing. Okay, save. And when you're ready, then you can press the little green arrow, and this will run through. I'm going to pause the video here while it runs, and then I'll be back once it's ready. Okay, so as you can see, slice timing's correction is now done. Slice timing done. So let's just list the folder and see what's in there. So what we'll see is we have our slice timing map that we saved, our T1, our task map, which came from setting the origin, I think, and then we have this file here, atask.nii. Okay, so that's the slice time corrected data. So it's the same functional data, but it's been resampled so that each volume represents the data as it would if all the slices have been collected at the same time as slice 2, which was our reference. Okay, so now that we've done that, there's nothing else to see other than the fact that the file's been created. We'll move on. So the next thing we have to do is correct for head motion. So when people lie in the scanner, they very rarely stay completely still. So you can see here, if we're acquiring images over time, people start moving their heads left and right. And that's a bit of a problem. So people can move in 6 directions, or 6 manners, I should say, 6 ways. It's rigid body transformations. They can move in the X, Y, and Z axis, and they can move around the X axis, which is pitching the head forward. Okay? They can basically rotate around this. This is pitching, the head goes forward. Roll, which is rolling around the Y axis, and yaw, which is twisting around the Z axis here. Okay, and that's a major problem for us. Sorry, let me just move to this presentation rather than this one. So yeah, as you can see, people, even though you're acquiring the data over time, people move their heads, and there's these 6 degrees of freedom that they can move for rigid body transformations. What we ultimately want to do is take the images, this is what the initial images, and this is when they've moved on the next volume, and we want to calculate the rigid body transformations to correct the images so they're all lined up again. And when we run motion correction, we'll end up with some measurement of the movement in the X, Y, and Z axis in millimeters, and the rotations around the X, Y, and X axis in radians, I believe, or maybe it's degrees, we'll see in a second. Okay? So the idea is basically to realign all the data to the first image, create a mean image, and realign the images to that. That's kind of the same as using a reference image in slice timing. The mean image represents the best overall position rather than having to move some images a very long distance. So we can put the slice time corrected images in, or the raw data, and we'll get back out a mean image, the original data with a modified header. We don't reslice the data over and over again, or if we said to reslice the data, look at some reslice files. One of the key points when you do imaging is that every time you reslice the data, you're cutting through cubes at angles, and the algorithm has to decide where the signal belongs. So you get inaccuracies called interpolation errors. And so we often try and avoid to resampling the data over and over again. And you'll see that in a second. Okay, so this is the instructions for doing it. You can pause it if you want to look at it. Otherwise, we're going to do it now. Okay. Sorry. Oh, I'm just messing this up. Ah, there we go. Okay. So you can click up here, realign, estimate, and reslice. Like this. actually we'll do that way. I'll show you the batch in a little bit later. And you get this option. So again, there's an X here. So we'll say new session. And this will ask us for our data. And again, it's the functional time series we're going to give it. But this time it's going to be the slice timing corrected files, the A task files. So again, don't click on the files directly. We need to select all the 500 files. Ooh, and just do AT. That gets rid of everything else. 1:300. So we want to select all these files. Right click, select all. And you can see the 300 files in there. Again, if there's anything other than that, go in, you can right click, unselect all. I should have done that first, just to demonstrate. So if you make some mistake with it, you can just go unselect all. A task, 300. Right click, select all. Okay. And the image quality just says what percentage of the voxels do you want to track. 90% is good enough. If you can go to 100, you can, but you can go to 100, but it just takes longer. It doesn't give you much better performance. This is how far apart the voxels you want to track are. It does a little bit of smoothing. We want to do number of passes is register to mean, which means it's a 2-pass system. So what it does is it registers to the mean, registers to the first image, creates a mean, and then registers to that. And this just tells you how it's going to reinterpolate the data. Okay, which is here as well. Okay, so the first thing is, as I said to you before, we don't want to reslice all the data all the time. We do need a mean image, but what we'd like to do is estimate the movement parameters and just save them for later on. So we'll say mean image only for reslicing. So this will reslice the image to give us a mean, but it won't reslice all the other files to correct for motion. It'll store the parameters that would need to be applied, but it won't apply them till later on. And with that, we can save the file. Hopefully, here we go. And we call it realignment. And again, I'm going to press play, and then I'm going to pause it while it runs, because it seems to be taking quite a while to run. I'm recording this at home, so that explains it. Okay, so press play, and then I'm just going to pause the video. Okay, so this should be working now. Okay, great. So as you can see, it's now finished realignment. So again, realignment, estimating, reslicing done. If we type in ls, we'll do ls minus tr, I'll just skip them in order. The new file that's been created is this image here, the motion parameter, the PS file. Yeah, they're not going in the way I'm expecting them to, but that's fine. Okay, so we got a mean task image, that's our mean image. We've got this file here called the realignment parameters file, RP. So this is a text file containing the parameters, 6 columns, 3 translations in the X, Y, and Z axis, and 3 rotations around the X, Y, and Z axis. And actually those values are seen in the graphics window here, if it actually loads it. There we go. So these are the values that are actually in that file. So movements from volume to volume in the X, Y, and Z axis, and the rotations around those volumes. So although these values look quite big, you actually see they're quite small movements. The general criterion is any movement greater than 1 voxel size is considered a problem. So if someone moves more than 1 voxel, so that's 3 millimeters. So if a person moves over 3 millimeters over the run of the scan, it's generally considered that the data is either junk or needs some special treatment. So yeah, so we get a realignment parameters file, a mean image, the PS file which holds that picture, the graphics window. But our A task file, these ones here, they've had their header altered, so they now have the information stored about how to correct for motion, but they haven't been applied yet to the data. The data hasn't been resliced to be corrected for motion, but that information is saved. Okay, So now we'll begin with the next step. So after you've done motion correction, so again, just remind you that's there if you want to read it. So we have the ATAS file with the realignment parameters stored, the RP text file, the mean ATAS file, and the spm.ps file. Okay. If you reslice the data itself, you would have an R prefix on it. Okay, and this is just to tell you, there's no hard or fast rule, but generally 1 vox is considered the limit for reliability. Spikes are more of a problem than drift, but they need to be modeled particularly, and there are some toolboxes to deal with this sort of issue, but they're not SPM tool, they're external toolboxes. So the next thing we're going to do is we want to normalize the data to standard space. And I'm going to quickly just explain why we're doing the way we're doing it. So the standard thing is we want to warp the data into a reference space so we can combine images across peoples. We can draw population inference. The problem is everyone's brain's different size and shape, and so it's not an easy process. So we generally do 2 things. We do affine transformation, so we take the subject's image and we get it roughly in the right shape and size for our template. Here's a template made from 152 subjects. So we move it in the X, Y, and Z axis. We rotate around the X, Y, and Z axis. We stretch it in the X, Y, and Z axis, and we shear it or twist it, pull at it at different corners to make it fit the template pretty well. And then we apply these non-linear warps, these low-frequency warps that produce fields that distort the image locally. Okay. The first approach is really straightforward. You just take an image and you warp it straight to the MLI template. This used to be done. In fact, I did this for my PhD work. It's not advised anymore. So you get a normalized image like this. Okay, and then you apply those transformations for the rest of the day. So you take the mean image for realignment, you warp it, and then the parameters that come from this warping are then applied to your realigned data the rest of the time series. But one of the problems with this option is that whereas the template here is often, the template is often spin echo and doesn't have any susceptibility artifacts, your EPI image does. And therefore, when it tries to fit this onto the template, it twists and bends the front of the brain. So you can see there's a deformation here, the field is changing shape. Okay? And that means you actually stretch the brain to fill space where there is no brain, and you don't want to do that. You allow a little bit of warping, but that's basically make it look like the anterior cingulate is actually the orbitofrontal cortex, which you don't want to do. Okay? So another option is to co-register your mean image to a structural. Okay? And then use that structural to normalize the data. So the reason is because the structural image is very high resolution. It's got good grey-white contrast, and so therefore warping to standard space is relatively easy. So if we align our functional data with structural, then we work out what we have to do to get our structural into standard space. We can apply those images straight to those transformations straight to the aligned images. So exactly like this procedure here, where we take a mean image and we warp it to a template and we apply those parameters then to our functional data that are already in alignment with the mean image. If we align our data with the T1 and then warp the T1 to standard space, we can apply those transformations directly to the functional data. So the first step for this is co-registration. And this we take a structural image as our target, or reference here as it's called. The source image, which is the image that's moved around to match the image, to match the T1 or aligned to the T1, is the mean image from realignment. And then because we want to keep all our functional data in line with the mean, so it gets moved onto the T1 as well, in the others files we enter in the functional data. And what we'll get out again are the files with altered headers. Again, we're trying to avoid reslicing the data over and over again. So we'll get out some data with altered headers but not being resliced. So let's go and do that now. Okay, so if we click co-register, in this case we're going to do co-register only, not reslice or estimate reslice, so co-register only. And this will open the batch window for us, hopefully. Okay, so the reference image, as it says, is the image that is assumed to remain stationary. We'll take the structural. Now the reason for doing that is twofold. It's best to move low resolution images onto high resolution images. That tends to go better. The other thing is you often have multiple functional data sets and only one structural. So if you leave the structural in the same place, you can always use the same normalization parameters for each functional data set by aligning them with the structural. So I always use the T1 as my reference. So reference, pick your T1. Now this is where we're going to be aligning these images, and this is where most pre-processing goes wrong, and that's why we set the origin on the images to align them. When you do motion correction, you're actually doing the same thing. You're aligning the images to each other. But because they're the same image quality and the same grey-white contrast, you basically just have to subtract one image from the next and get the mean square error and just progressively move them until you get the minimum mean square error. With the T1 image and the function data, they look very different, and therefore it's a more complicated process. Okay, so the source image is the, as it says here, if it'll move, is the image that's jiggled about to match the template. So we specify that, and that's going to be our mean image. So we'll take our mean image here. And the last thing is the other images. So these are the images that remain in alignment with the source image with our mean, which is what we want. So we're going to specify, and again, we have to filter and take all 300 volumes. That's important. So if you applied it just to the first, if you just selected the file directly, you'd alter the first file but not the rest of them, so it would no longer be in alignment with them. And then 1:300. Oh no. 1:300. Right click, select all. Done. And that's it. So we can save this again. And we'll call this co-register. And then we can press play. And again, I'm going to pause this video once I've pressed play. And when we come back, you'll see the results. Ultimately, the headers will be changed, but there'll be no new files created. So press play. You see it started. And I will. Okay, so as you can see here, let me just check this is working. Yeah, okay. So as you can see, the co-registration is finished. So it's co-register estimate done. And the graphics window, you can see here. Now, this image is basically all the voxels in the T1 correlated with all the voxels in the mean. In an ideal world, if it was a T1 versus a T1, this line would be close to like that. The truth is, because you can see the images are very different, there's no skull, the grey-white contrast is quite different, the resolution is quite different. These things don't look great. They don't look particularly informative, to be honest with you. What you can do, though, is, however, is click on the image and check that the image is basically aligned correctly. Let's click on the edges of the brain. And as long as they kind of marry up, which they seem to, yeah, you can see here. These look pretty well aligned to each other. Okay, so just check around a couple of things, but that's in essence it. All right, so we now have a functional data set that's co-registered to the structural image, but we now need to estimate our normalization parameters. So let's go back to our slides. Right. So what we're going to do is we're going to skip normalization because virtually nobody does that anymore. There's a button called normalize, but it's almost never used. I'll leave the slide here for a second if anyone wants to see it. The vast majority of people do normalization via a process called a unified segmentation, or what's above that is Dartel, which I may do another video on at some point. So we're going to move on to that. We use normalize method number 3, which is unified segmentation. And that is the structural image, the SPGR in this case, goes through segmentation, and the resulting normalization parameters are applied to the co-register DPI data. The strengths of it are you get a very good estimate of normalization parameters because the structure is segmented into grey-white tissue classes, and that constrains the local warping. the weakness is if the FMI data doesn't co-register well, then you have that issue. But we set the origin on the images, and that seems to avoid any real problem. And they do look like they've co-registered correctly, so we're happy enough to go forward. Okay, so we segment the images. This gives us a grey, white, and CSF segments. It actually gives us 3 more out of that, but that's irrelevant. We don't actually care about those in this case. You need them if you're going to do a VBM analysis. What you get out is these spatial normalization parameters. Now in SPM12 there's a deformation field rather than a seg-SN. It's called a Y prefix, and you'll see that in a second. And we're going to then apply that to our data using normalize. So in the old days you used to normalize, normalize, estimate, and apply, or estimate and write. But now we just normalize and we apply these transformations from the segmentation. Okay, so first step is the segmentation. And this here, I'll just leave this on the screen for a second, and then we'll go through and do it. And you'll see we're going to get segmented images. Okay, on the graphics window. Okay, so to do this, we click on segment. And here we just give it the T1 file. You can give it multiple T1s if you want as well here. So this is going to take our T1 file that our images are co-registered with. Sooner or later. And that's actually all we need to do, except change so it saves out the deformation field. So these are the warp fields that warp the images into standard space. Forward warps from native space into standard space. Inverse warps from standard space back to native space. If you want, you can create both. So the forward warps have the prefix y underscore, and the inverse have iy underscore. Okay, and that's it. You basically just give it your structural, and you make sure it saves the deformation fields. If you were doing Dartel, for example, you could turn on Dartel imported. Or if you're just doing VBM and you want to warp the images, you can produce the modulated and unmodulated images. If anyone has questions about that, I'm happy to talk about that. Okay, so we'll save the batch again. And we'll just call it segment. And then we'll press play, and I'll pause the video again. Segment. And with that, we press play. And I shall pause. Okay, so as you can see, segmentation is now complete. Yes. This is working? Yep, it is. Okay, fine. Sorry. So segmentation is now complete. If we type in ls, we'll do ls minus TLR. Okay, we can see now that we've got the segmentation file that we saved. We've got segmentation parameters as a mat, but we've got the inverse deformation field, so warping from M&I space back to standard space. We've got the 5, so C1 is grey matter, C2 is white matter, C3 is CSF, then 4 and 5 are inside the head, dura, skull, and Y is the forward deformation to warp the images straight into standard space, M&I space. Okay, so we've covered that. Let's have a quick look at the code. Okay, so the next we want to do is we normalize the data. So we click normalize, and we're going to do write, and we'll give it the deformation field. These things are slightly incorrect, but that's okay, because we don't give the seg-SN, we give it the deformation field. So normalize, write. So normalize, write, and we get this thing. So again, where there's an X, it needs information, so you say new subject, deformation field, specify. So we're just selecting our deformation field. and it's already filtered it for the Y file. Okay, it didn't do a little hat, and that's why it shows the I as well as the Y. So we'll click the Y because we want the 4 deformations, and then we need to give our FMI files. So if you remember, we need to filter the files again. So these files are the slice time corrected files that have been through realignment and co-registration, but the files were only segmented or only resliced at slice timing correction. So they're still the A task, which is the output from slice timing correction, but their headers have been altered to hold the realignment parameters and the co-registration parameters. Select all. We press done, and that's it. We can save this. So and we'll call it normalize. Okay, if we have this muscular. Okay, the normalized file's there, so we can press play on the batch editor, the little green arrow. And again, I'm going to pause this and let it run through. Okay, so we can see now that normalization is done, normalization write is done. So if we ls, muscular, we now have a WA task, or W stands for warped. So warped slice time corrected files. Just so you know, we've also got, these have also been motion corrected and co-registered the T1 before we applied the deformation fields. Okay, so data, we've got one last step of pre-processing to do, and that is to smooth the images. So smoothing is basically blurring the images. You take some images like this, and you apply some 8mm smoothing, and you get something like this. Now, the typical way it's referred to is FWHM, stands for the full width at half the maximum height. So if you take a smoothing kernel, which is this shape here, if you go to half the height and you measure the full width, that gives you an estimate of the amount of smoothing that's going to be applied. So if we applied smoothing to this dot here, it would end up looking like this. So it's been smoothed by something like that. Okay? Now we smooth for a number of reasons. 4 in fact. One is to deal with inaccuracies in spatial normalization. The other is to deal with the fact that everyone's brain, sorry, that's gone, but it's going by. So the first reason is because to deal with inaccuracies in the normalization. Although the algorithms are pretty good, they can be slightly inaccurate in some places. To deal with differences in structural, basically everyone's brain is slightly differently structured, so there can also be some residual effects of that. So blurring the images kind of corrects or masks out that effect. The other 2 reasons, one is to increase the signal to noise ratio. When you smooth an image, you increase the signal to noise ratio. And basically you average the noise out. If the noise is really random, it should be averaged out. And the last thing is you make the assumptions underlying multiple comparisons correction in using Gaussian random field theory more likely to be correct. One of the assumptions is that the image is a uniformly smooth field. But of course, with brain anatomy in different regions, the small structures, big structures, the field isn't uniformly smooth. So we apply smoothing, and that makes that assumption more likely to be correct. So they're the 4 reasons for using it. And it's very simple. You basically put in the images you want to smooth. You specify how much smoothing you want in the X, Y, and Z axis. People generally do the same in all 3 axes. And you end up with a file with a prefix S. So let's do that now. Oh, sorry. So we click smooth. And again, we're going to select our WA files this time. These are our normalized, slice time corrected, motion corrected files. So we put a prefix here of WA. And that identifies the smooth normalized files. Sorry, our normalized slice time corrected. And then we say 1:300. right click, select all. And again, we're going to do 8 by 8 by 8 standard. The general guidelines, it should be about 2 to 3 times the acquisition voxel size, which is usually kind of 3 millimeters. There is also one other factor I haven't mentioned, which is called the matched filter theorem. It suggests that the amount of smoothing, or the amount of the size of a filter, which is what smoothing is, should be dictated by the size of the effect you expect to see. So if you're interested in the amygdala, smoothing the image by 10 by 10 by 10 here would smear the signal from a small structure out over a larger area, and you'd be unlikely to find that effect. However, if you're looking for the prefrontal cortex, smoothing by 3 millimeters is basically going to keep a lot of noise in there and weaken your sensitivity. So 8 by 8 by 8, 8 in each of the 3 axes is a good compromise. But if you're interested in the amygdala, you might want to drop it down to 6 by 666. Very few people now go to 10, 10, 10. It's just not done so much, but it could have been done. Okay, so let's save this. We'll save this file as smooth, and then we'll press play. So we'll pick our, oh yeah, we're going to call it smooth. And then we can press play, and I'll pause this then once I've done that, and I'll be back to you once it's finished. Okay, so as you can see, smoothing is done, and if we just do ls, you see the SWA task is there. Okay, so the next step is to do some QA quickly. So the first thing to do is to check the motion parameters quickly. So as you saw, the RP file is specified up here, RPA text file. So we can load this up quickly. You saw the graphics that was created before, and that's saved to this PS file. But if you don't want to have to open a PostScript file, you can just say RP equals this file. Okay, and then RP equals text read RP. And that's all the data. Create a figure, plot, RP, all the rows for the first 3 column, 1 colon 3.